Technologies have significantly improved our daily lives, making us more efficient. We require electronics with ever more power, storage capacity, and speed at an ever-decreasing size. Producing the high-performing microchips needed for this requires utmost advanced manufacturing processes. So, how is a microchip built? Microchips are produced out of silicon wafers, very thin plates of purified, shaped silicon, an ideal material for making transistors. After various treatments of the wafer, a photoresist coating, highly sensitive to light, is applied on the wafer. A UV light of extreme intensity is directed towards a mask and onto the wafer at an extremely small size. This causes a chemical change in the coating that is exposed to the light. The soluble resist coating is washed away, cleaning the wafer surface to start utmost precise chip building processes. It's when creating the 3D structure of the chip that our expertise in plasma control is crucial. In a vacuum chamber, the wafer is placed on a pedestal. The chamber is first pumped and then flushed with different possible gases. We then ionize these gases with RF power to ignite various species of plasma. To build the chip structure of the wafer, plasma ions react on the wafer's surface to selectively remove and deposit material. This is done hundreds of times until the 3D structure of the chip is created. To enable that at nanoscale, this process requires a highly precise control of the RF power, which is produced by a high-frequency generator. When connecting the generator directly with a coaxial cable, the RF power is reflected, which is why it requires a so-called matchbox to transform the RF impedance of the chamber to the coaxial cable. Since the impedance of the chamber is changing during the process, variable vacuum capacitors are used in the matchbox for automatic tuning. One wafer can now contain thousands of identical chips that need to be separated. In the traditional process, the wafer is precisely diced and chips are taken individually out of the wafer. For protection, the chip is packaged. In the conventional technique, chips are placed on a packaged substrate where they will be connected through soldered metal wires. After a certain number of optical and electrical probes, a molding process encapsulates each wired die in a protective plastic package. The chip is then ready for inspection. While traditional packaging interconnects the different chips on a board horizontally, new manufacturing processes improve downsizing by stacking them on top of each other, allowing for higher performance and smaller footprint. We call that advanced packaging or 3D packaging. This great advance also comes with challenges. Each chip is interconnected by thousands of wires and bumps, and the failure of only one interconnection could put in danger the entire module and ultimately create a defect electronic device. Because the chips are encapsulated, conventional optical inspection is no longer enough. It's where our X-ray technology comes in. To ensure zero default, the highest level of X-ray inspection is possible thanks to our precise X-ray sources, tubes, and generators. Active inside our X-ray systems and combined with highly precise imaging software, even the tiniest defect becomes visible. Our X-ray solutions can inspect objects that are many thousand times thinner than a human hair. And now, what if we could predict where the next defect may appear? By combining X-ray with AI, we are soon opening up the possibility to customers to predict and avoid issues during the manufacturing process, ultimately decreasing waste products and improving safety. No matter what the future of technology requires, should it be in electronics, automotive, aerospace, or security, Comet is ready for the challenge, led by experience, driven by curiosity. Comet.